For as long as I can remember, I've been intrigued by one thing. You will hear it as a car went by. If you drove down this road as those sirens went off, you would hear it too. What is it? It's the Doppler effect. Come inside and let me explain.
Here I am driving my car down the road at 40 miles an hour. As the car is approaching, the pitch of the horn seems higher, but as it passes, it drops dramatically. Matt's showing an ice cream truck jingle recorded on his megaphone. Notice the pitch as it is stationary. When I'm driving 40 miles an hour, it sounds a lot higher. And here it is at 40 miles an hour again. Notice how low it sounds once it passes. Here's another example of the Doppler effect. This time, I have a police siren at 40 miles an hour. Check out Penn State Hershey's Lifeline helicopter. Its back rotor is enclosed in the tail fin, so the air is chopped and it creates a distinct whistle. Listen to that whistle as Lifeline passes. It drums.
Up until now, the source of the sound has been moving and the observer has been stationary. Now, if the source of sound is moving at 40 miles an hour and the observer is moving 40 miles an hour in the other direction, it'll double the Doppler effect. It would be like a police siren passing a stationary observer at 80 miles an hour.
Turn it on! Get out the window! Get out the window. Whoa!
Hi, my name is Joe. I'm an amateur radio operator. My call sign is K3SZH. And I'll show you my satellite station via amateur radio and the Doppler effect of it. It's like listening to a fire truck. As it comes towards you, pitch is higher. As it passes you, the pitch is low or frequency. It's very similar to our amateur satellites, which are in elliptical orbit. As it's further away, the frequency is higher. As it moves down the orbit, it comes lower. And that gives you the Doppler effect. The lower orbit satellites relative to us move faster, so the Doppler compensation is greater. The satellites that are further out relative to us move slower, so the Doppler effect is less.
The Doppler effect works in ways you may think are not possible. What if the source of sound is stationary but the observer is moving? Will the Doppler effect work? Let's check it out.
Here's the siren at Paxlina Fire Station. Every Saturday at noon it goes off for 30 seconds. I'm going to drive by it at 30 miles an hour. You'll notice a difference in the pitch from the stationary observer and the moving observer. First, here's the siren from the stationary observer. Now here's the same siren, but as I'm driving in the car. Do you notice how the siren sounds higher? Doppler effect is visible when a duck is swimming in the water. Duck is kicking its feet underneath the water to move. That creates waves. Since the duck already has a forward velocity, the waves move more frequently in the front and less frequently in the back.
The same wave properties of the duck apply to sound. If the source of the sound is moving at 50 miles an hour, the waves in front of it will be closer together, more frequent, so the frequency is higher. Behind that source of sound, the waves are further apart, so the frequency is lower. Therefore, the pitch seems lower to the observer.
The frequency perceived by a detector is equal to the velocity of the detector relative to the velocity of the wave, divided by the velocity of the source relative to the velocity of the wave, multiplied by the wave's frequency.
If you think the frequency coming from the device is actually shifting as it goes by you, as in higher winds coming and lower winds passing, you're wrong. The frequency from the device is constant, always. Just the frequency that you observe is different.